when I put that in water, the pH goes up. Why does that happen? First of all, pH is a measure of hydronium ion concentrations. And hydronium ion, how many of hydronium ions does this make when it dissolves? Might have a trick question, wasn't it? It takes them away. Why does it do that? And we know that there's an inverse proportionality between the two, right? We know if hydroxide ion concentration goes up, hydronium goes down. We don't have that here, but one of the things that mathematical relationship says, that if one gets bigger, the other has to get smaller, huh? Okay? Now we can talk about the chemistry involved in why that's true. It has to do with this dynamic state of equilibrium that exists in water between hydronium and hydroxide ions. And it's not something that we're going to emphasize right now, other than the result of that equilibrium. In Chapter 18, we'll come back and visit this again and talk about why it is that we expect these concentrations to do what they do. Right now, we're just interested in the fact that they do what they do. So, when I add sodium hydroxide to water, what changes? Concentration of hydroxide increases, doesn't it? Doesn't that mean the concentration of hydronium decreases? And how do we get the pH? We take the molarity of hydronium ion, take the log change of sign, right? And if the hydronium ion concentration goes down, that means the exponent of 10 is more negative, which means when we take the logarithm is more negative. And when we change the sign, we get a number that's more positive, right? So the pH goes up. Yeah? Okay. Now, why would adding, no mystery then as to why adding sodium hydroxide to water makes the pH go up. No mystery as to why, if we add sulfuric acid to water, the pH would go down. Because what are we making when we add a strong acid like sulfuric acid? Hydrochloric acid, nitric acid, perchloric acid, hydrobromic acid. Those are ones that are listed on your table. No mystery as to why when we add this to water, we end up with more of these. Take the log becomes less negative, the pH becomes more positive, right? Excuse me, the log becomes less negative, so the pH becomes less positive, smaller, right?
Wait, would we be okay on like testing stuff to just say, okay, the hydronium concentration goes up, so the pH goes down, or do we have to explain how that affects the equation?
No.
Wait, what?
No.
Wait, what?
So it's okay to say that if the hydronium ion concentration goes up, the pH goes down. Okay? It's okay to say that. And it's okay to say that if the hydroxide ion concentration goes up, the hydronium ion concentration goes down, without having to explain why. Okay? All right. But sodium carbonate. I got some of that too. Sodium carbonate. When I add that to water, the pH goes up. Don't see any hydrogen ions. Don't see any hydroxide ions. What would a solution of this contain? Sodium ions, aqueous sodium ions, and aqueous carbonate ions. By the way, you're not really tempted to write ions like that, are you? And then I have people all the time write this. Do I make two of them? A 1 molar solution of this, does it contain 2 of these and 1 of those? It does contain 2 of these for every one of those, and if this were a chemical equation, I'd write in coefficients, wouldn't I? Right? But it's not a chemical equation, so I don't write coefficients. The coefficient is not part of the formula for the substance, for the ion, right? You can get away from doing that. Okay, so if I have a solution of sodium carbonate, it contains these two ions. Why would either of those ions affect the pH?
Carbonate's a stronger base than hydroxide.
How do you know it's a stronger base?
The chart.
It goes on the chart, that's right. Don't you have a list of bases in order of strength? Yeah. You've got a list of acids in order of strength. Also, I'll have a list of bases. And it's not a complete list, an exhaustive list, but carbonate ions are on there, aren't they? And what would happen if you put a carbonate ion with a water molecule? Could an acid-base reaction occur?
Yes.
What are the two conjugate bases that are competing? What are the two bases that are competing? Carbonate ion and the hydroxide ion. Which one's a stronger base?
I don't even see carbonate.
Isn't hydroxide the stronger base? They're listed over there. What does that mean? Does that mean that this will never take a hydrogen ion away from that? It's not what it means. It means that it won't take most of them away. But will it take some of them away? And if I take some hydrogen ions away from water, what do I make some of? Hydroxide ion. And if I increase the concentration of hydroxide ion, what happens to the hydronium ion concentration?
What?
Now you will need to be able to explain that. Carbonate ion is a strong base. It will take at least some hydrogen ions away from water. That will increase the concentration of hydroxide ions. And if you increase the concentration of hydroxide ions, you decrease the hydronium ion concentration and you increase the pH. So adding a base like this is almost like adding sodium hydroxide to water, isn't it? Because you increase the hydroxide concentration even though there's no hydroxide ions in that compound. Yeah? How are we doing? Now, that is a base in the Arrhenius acid-base system, isn't it? A supplier of hydroxide ions. In the Bronsted-Lowry acid-base system, that's a base, isn't it? But then, so is that. Right? In Arrhenius and Bronsted-Lowry acid-base theories, the acids are identical. The same group of compounds are acids in Arrhenius acid-base theory and in Bronsted-Lowry acid-base theory. The difference between Bronsted-Lowry acid-base theory and Arrhenius acid-base theory is the basis. Bases are limited to compounds that contain hydroxide ions in the Arrhenius acid-base system. So Arrhenius acid-base system would not explain why the pH goes up when I add this to water, because it doesn't contain hydroxide ions. Get it? Arrhenius. Old-fashioned. Don't like it. Doesn't help. It's great for the 8th grade. It's great when you're just learning about pH and acids and bases. Okay? But it doesn't help us very much. We all right? Okay. Now the question is, when I add that to water, the pH goes down. Ferric chloride or iron 3 chloride. When I add that to water, the pH goes down. Let's start with basics. When I dissolve this in water, what do I get? I get these ions, and I get these ions, I get those ions, right? Yeah? Let's start with the negative ion. What can that do for us? Ooh, Chloride, base, right? Every negative ion can be a base. Very weak base, among the weakest that exist, huh? So do we expect chloride ions to take hydrogen ions away from water? We do not, huh? If it happens, it only happens rarely. We don't expect chloride ions to do much to this solution. Okay? So what can that do? What does that have an attraction for? Hydroxide ions, huh? Take a look at your solubility rules. If I put iron 3 ions together in the same solution as hydroxide ions, what happens?
That's what I was getting.
Precipitate forms. What does that mean about the attraction for iron 3 ions and hydroxide ions? Pretty strong, huh? So when I put ferric ions, Fe plus 3 ions, into water, it starts grabbing a hold of hydroxide ions. Does it precipitate form? Actually it does. A small amount. The solution gets a little cloudy. Now keep in mind, what is the concentration of hydroxide ion in pure water?
1 times 10 to the negative 7th.
Not a lot of hydroxide ions in pure water, right? So we don't get a lot of precipitate because there's not a lot of hydroxide ions. But what happens to the concentration of hydroxide ions when I put those ions in water? It goes down because the iron starts grabbing a hold of them. Yeah? And if hydroxide ion concentration goes down, hydronium ion concentration goes up, doesn't it? And the pH goes down as a result. Are you with me? So the solution becomes acidic. Is that an acid? Not in the Bronsted-Lowry sense, it's not. Lewis. In Lewis acid-base theory, that's a Lewis acid. Why is it a Lewis acid? Lewis acid-base theory says Lewis acids are not proton donors, but electron pair acceptors. And who, for instance, has electron pairs? Right? In Lewis acid-base theory, which we got to, first day we talked about this, right?
Yeah.
A Lewis acid, a Bronsted-Lowry acid is a proton donor or a hydrogen ion donor. A Bronsted-Lowry base is a hydrogen ion acceptor or a proton acceptor. Lewis acid-base theory turns it around. Instead of donating hydrogen ions, they accept electron pairs as an acid. A base, instead of accepting hydrogen ions, is a donator of electron pairs. Right? Now, the nice thing is that all the Bronsted-Lowry bases, which we think of as proton acceptors, what is it about them that makes them good at proton accepting? Electron pairs, huh? Unshared pairs of electrons. Sulfide ions, hydroxide ions, carbonate ions, phosphate ions, chloride ions, nitrite ions. They all have electron pairs. And that's where the accepting of protons or hydrogen ions happens, right? So is that base a hydrogen ion acceptor or a provider of an electron pair? It's either one, isn't it? Both. So a Lewis base and a Bronsted-Lowry base are the same thing.